This is a specific heat capacity question. We're using the equation energy equals mass times specific heat capacity times the change in temperature. Now we don't know the mass at this stage. We've been given the volume of the container and therefore the volume of the water, and we've been given the density of the water. Now the density has been given to us in grams per cubic centimetre, so let's stick in centimetres for now to work out the volume. So it has a square base of side 10 centimetres, so our volume is going to be equal to 10 times 10, and a height of 15 centimetres, so times 15, which will give us, that's 100 times 15, which is going to give us 1500 centimetres cubed. Now the density of water is 1 gram per centimetres cubed, so that means we have 1500, that means our mass of water there is 1500 grams. We now need to convert that to kilograms because our specific heat capacity has been given to us in kilojoules per kilogram per Kelvin. So our mass is 1.5 kilograms of water. Okay, so let's look back to our equation again. E equals mass 1.5. Specific heat capacity is 4.2 kilojoules. Just remember, so our answer is going to come out in kilojoules, or if you like, we can put in times 10 to the power of 3 there, just to make sure we don't make any mistakes with that. Multiplied by our change in temperature. Well, we're going from 20 to 100, so we use that. So it's 80. So we have 1.5 times 4.2. So that's going to be 6.3 times 10 to the 3 times 80, which when you've done your sums comes out as 504 times 10 to the 3, or let's put it back in kilojoules, 504 kilojoules. That's the answer to our first part. The next part of the question tells us that the explorer has gone up Mount Everest and she's found that the boiling point of water decreases by 1 degree C for every 300 metres that she rises up the mountain. Very quick question here for 1 mark. What physical effect causes this reduction in boiling point? Well, boiling occurs when molecules of water are able to leave the surface of the water to become a gas. That is much easier to do when the air pressure around it is lower. There's less pressure keeping the molecules within the liquid. So it is due to the decrease in air pressure up the mountain. Now another specific heat capacity question here. So once again, E equals mc delta theta. Delta theta is our change of temperature. Now the tricky thing to work out here actually is our delta theta. So the maximum temperature that we want would have been 100 degrees, but we can't boil water to 100 degrees up a mountain, so we need to work out how much lower that is. So the boiling point should have been 100, and from that we need to take away the effects of the air pressure, so that will be for every 300 metres, so 6,000 divided by 300 will give us the number of degrees that the boiling point will have reduced by rising 6,000 metres. So that's our maximum temperature, and from that we need to take away our starting temperature, which is 10 degrees C in her tent. And let's sort that out a little bit, so that becomes 100. Take away and cancel some of these zeros. So that's 60 over 3. Take away 10, so that's 100, minus 20, minus 10. So the required temperature rise is 70 degrees Celsius. Okay, so now how much energy do we need? So let's go back to our equation. E equals the mass. Now here we have 100 grams, so that's 0.1 kilograms, multiplied by our specific heat capacity of water, which is 4.2 times 10 to the power of 3, multiplied by our temperature change of 70. So that's the same as saying 4.2 times 10 to the 3 multiplied by 7. Multiply the 0.1 and the 70 together. And after you've done your long multiplication, you'll end up with an answer that is 29.4 kilojoules. 29.4 times 10 to the 3 joules. Disaster. The stove is only producing 50% of the power that it did at sea level. So if it took 15 minutes to reach boiling point at sea level, how long will it take to reach to boil the water up the mountain? So we can begin by working out the power of the stove to start with. So power equals energy divided by time, and the energy required at sea level was around 5 times 10 to the power of 5 joules. We can look back to the first part of the question for that, and we need to divide that by the time in seconds, so it's 15 multiplied by 60. So that's 5 times 10 to the 5 divided by 900. So that's 5 over 9 times 10 to the power of 3 watts. That's the power at the start. Now, however, if you've got a problem, it doesn't work as well as it did. So the new power, power 2, is going to be half of that amount. So that's going to be 5 divided by 18 times 10 to the power of 3 watts. We're just going to keep it in a fraction to save us doing that calculation. So let's rearrange the equation here to find time. So time 2, for completeness, let's call it 2, equals the energy 2, that's the energy up the mountain, divided by the power of the stove that's now faulty up the mountain. Our energy, we recall from earlier, was around 30 kilojoules, so that's 3 times 10 to the power of 4 joules. And our power is 5 over 18 times 10 to the 3 watts. So let's bring that 18 up to the top, and that will give us 3 times 18 is 54 times 10 to the power of 4 divided by 5 times 10 to the 3. Now we can obviously do something with these the standard form, so we'll end up with 54 over 5 times 10 to the 1, which is going to be around about 110 seconds.